everybody hear me?
Yeah.
Okay. Okay. My name is Daisuke, and today I would like to present my ongoing work with Jim McElwain and Herbert Huppert, who are my PhD supervisors here in Cambridge. I will begin by formulating the problem that I would like to address. I will then outline the experimental setup that we have next door down in the basement, and then I will present the results of two representative experiments that have been conducted. The problem that I would like to address is the following. Consider a point source on a rigid incline without any side walls, from which granular material is supplied at a steady rate. It has been determined that over an intermediate range of slope angles, a dense granular flow develops and forms static levees. I will talk about levees in a moment. It has been determined in a separate set of experiments that the flow of spherical beads becomes thinner and wider with a relaxation time that is extremely slow. I would like to address how, as a result, what happens is that the resultant flow becomes very thin, and the thickness becomes comparable to a critical thickness called H stop, below which no flow occurs. So what I would like to address today is how a flow rule like this, which successfully describes very deep flows down an incline, breaks down in the shallow layer limit as the thickness approaches H stop. I would also like to address what the long time limit of this system is. So the picture on the left-hand side shows a rigid incline of length 3 meters and width 1 meter. The picture on the right shows a magnified view of this region near the top of the incline, where there is a hopper and a delivery tube and a turquoise-colored piece of foam. What this allows us to do is it allows the granular material to effectively be introduced onto the slope from a point source. The incline consists of glued sand, which has a mean grain diameter of 0.6 millimeters, and there is a laser scanner over here, which measures the thickness of any sand pile that develops on the slope. There is a linear traverse system over here, which moves the laser scanner to its desired position. I'm now going to show you a video of an experiment where 53 grams of sand is introduced onto a slope of 32 degrees to the horizontal. This video is being played at 3 times the original speed. And what we see here is a continuous stream of sand down the incline. And this is a planned view of the flow. If you look carefully at the margins, the sand is not flowing at all. These are the levees that I was referring to earlier. Now I'm going to show you a video of a separate experiment where the flow rate is reduced by approximately a factor of 3 to the previous video. All the other parameters are fixed. So again, this video is being played at 3 times the original speed. What we now see is a rather different behavior. The flow is discontinuous in the sense that the system consists of a static deposited layer onto which successive avalanches arrive and flow on top of them. So these, so near the source, an avalanche is triggered over here, and then it effectively travels like a traveling wave down the incline. There were other experiments conducted on steeper slopes, what happened there was that something like a roll wave instability developed. This is something that I will not be talking about today. So going back to the first video, this is the experiment where a continuous stream of sand developed down the slope. This plot shows a cross-section of the flow approximately 2 meters down the incline. And these different lines correspond to the sand pile at different times. So initially there is no sand pile at all. At around 2 minutes after the experiment has started, the flow reaches this 2 meter mark and has a slight hump at the margins. These correspond to the levees, the static levees that were shown in the video. At consecutive times, the thickness decreases very slowly, while the width of the sand pile remains fixed. This is rather surprising given the fact that the flow across this sand pile is steady. At later times, this is again the same plot, the plot of the cross-section of the flow, but at much later times. We can see that the sand pile at 40 minutes, 50 minutes, and 60 minutes after the experiment all coincide. And this indicates that the system has reached a steady state. The steady state consists of a free surface that is approximately, that appears relatively flat. This plot shows the cross-section of the flow at very large times, 70 minutes after the experiment has started, at different extents down the incline. This shows that the flow has become fully developed in the sense that the thickness and width of the flow are uniform down the incline. I would now like to talk about the second video that I showed you earlier. This is the situation where avalanches are triggered. This plot shows the mean thickness of the sand pile approximately 2 meters down the incline, and how that evolves with time from the moment when the flow reaches the 2 meter mark. The local maxima correspond to those times when an avalanche arrives at the 2 meter mark, and the local minima correspond to the static deposit that is left behind the avalanche. The top plot is effectively the same plot as the previous slide, but it's looking at the evolution for the first 2 hours of the experiment. What is interesting here is that the system appears to reach a periodic state in the sense that the thickness of the deposit behind the avalanche and the thickness of the avalanche appear to tend to a constant value respectively. The plot on the bottom of the slide shows the interval between successive avalanches, and it shows that after a transient phase for the first hour or so, where the period appears to decrease slowly, there is a long time periodic state where the period of the avalanches appears to tend to a constant value. So these two plots indicate that the size and the frequency of the avalanches are not unpredictable. They are regular. So in conclusion, I'd like to say that the flow of sand on a rough incline experiences a slow transient phase before reaching equilibrium in the long time limit. The long time limit consists of may reach a steady or a periodic equilibrium. Now in the future I would like to vary the inclination angle and the flow rate at the source over a larger range to determine how the thickness and the width of the flow depend on those parameters. Thank you very much.
I guess I'd like to draw out your comment that you made at the outset about how you think that this is shedding light on what happens to the flow rule at small values of H. I guess the implication is that at these low flow rates, you are not able to sustain flows with H greater than H sub S, and therefore the system goes into a periodic state.
That's absolutely correct.
Which suggests, in a way, it's a triumph of the flow rule, because the local states, either flowing or not flowing, might be perfectly consistent.
Yes, that's absolutely correct. Yes, I agree. So what happens? So if going back to this, the flow rule here, this is effectively a Froude number, and if and what happens? So what happens is that if we impose a flow rate at the source that is too small, below some critical Froude number, then we cannot achieve a steady flow, and so it switches to something intermittent.
If I remember well, in Duboff et al. Work, they were observing a slow creep.
Yes, that's correct.
And you do not observe that in the long time limit.
Well, so the experiments that were conducted here were using spherical glass beads, whereas in our experiments we used sand, which is different, and
you think that's one of the different?
And so what we found in our experiments was that the thickness was slowly decreasing, but the width of the sand pile was not increasing at all.
Yes.
So is the implication that your avalanche flow rate matches your critical flow rate?
Sorry, could you repeat the question?
Yep. So when you have an avalanching situation,
Yes.
does the instantaneous avalanche flow rate match the critical flow rate that you have in your equation?
Oh, that is yet to be verified, but that is something that I would like to test.
Nico?
What sort of variation in particle sizes do you have?
The sand that I used in the experiments are approximately, well, not, I think over 90% of the grains are, I'm just trying to remember the specification of the sand. It is, I think over 90% of the, over 98% of sand lies in the range from 300 to 600 microns. But I can give you the exact figures.
Yeah, do you think size segregation is important?
That's difficult to conclude from our set of experiments, but there is and perhaps segregation might favor the formation of levees at the margins. But my view is that it is not a necessary condition. I think that these levees will form even with monodisperse grains simply because of the fact that when the flow reaches a critical thickness, then it can no longer flow.
Have you read the material of the science with, say, with respect to internal angle of friction? Does that play a role?
Sorry, could you repeat?
Internal angle of friction of
Yes.
the material, does that play a role in the phenomenon?
Well, I haven't conducted any experiments with other materials, so I don't know if I don't know if we'll see the same phenomena with other particles, but I guess
I expect that the beta may depend on the parameter beta.
yes, absolutely. The difference. So I guess what the dependence will appear in this expression called H stop.
Was there one last question? Please.
Yeah, in the long time limit, you see that the levees are somewhat less pronounced than in the slides you've got there. Do you have an idea of the mechanism? I mean, are they being eroded by the flowing material, or is the flowing material building up over the top of them? Or?
So the difference between the previous slide and this slide is that here the levees are less pronounced, and I guess the only possibility for that to happen without the width increasing is that without the width of the sand pile increasing is that the static levees, some of the static grains in the levees is being eroded and rejoins the flow.